Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss the fourth order Runge-Kutta method. So in this topic we will describe the fourth order Runge-Kutta method, and this is by estimating and averaging slopes. We will look at the technique visually. We will see that the error is order h to the 5 for a single step. We will look at two examples for a single step to see this. We will see how to apply this method under multiple steps, looking at an implementation in C++. We will look at two examples of using multiple steps, and then we will compare this algorithm with Euler's methods and Hoyne's method. Let's recall again that simple Riemann sums approximate an integral with a single function evaluation. The value of the function changes across AB, and locally a function will probably be behaving as if it was quadratic. Consequently, Simpson's rule integrates an interpolating quadratic across the interval, with the points being the two endpoints and the midpoint. This gives the approximation of the integral shown here. So notice we have a weighted average, 1/6, 4/6 for the point in the middle, or 2/3, and 1/6 for the last point. Now you'll recall that Hoyne's method used two slopes. So starting at the initial point, we follow that slope out a distance h. That's our first approximation. We calculate the slope at that point, and then we take the average of the two slopes and follow the average slope out a distance h. Just like with Simpson's rule, we'd like to take a few more samples of the slope across that interval. We are now going to introduce fourth order Runge-Kutta. This is an algorithm for approximating a solution to an initial value problem, one that is very accurate, but we will not be doing the error analysis in this course. Instead, we will simply present it. So, as with Euler's method and Hoyne's method, we calculate the slope at the current point. Let's assign this to S0. Next, let's follow that slope a distance h over 2. So now we're at the midpoint between the current t sub k value and the next t sub k plus h value we'd like to approximate the function at. All right, so we'll follow that slope out. Now we have a new slope at that point. Let's follow that new slope out a distance h over 2, and once again calculate the slope at that point. We'll call that next slope S2, and then we will follow that slope out a distance h. So there we will calculate the slope at that third point, and we will call that slope S3. We now have 4 different samples of the slope, one at the left-hand endpoint, 2 samples in the middle, and 1 at the right-hand endpoint. The formula for fourth order Runge-Kutta is shown here, where we take a weighted average of the 4 slopes. Notice the similarity with Simpson's rule, because we have 2 samples of the slope at the midpoint. Notice that the combined weight of those 2 samples at the midpoint are 4, similar to that of Simpson's rule. Visually, we will proceed as follows. We will calculate the slope at that point. We will go out a distance h over 2. We will sample the slope at that point, and then we will follow that slope out a distance h over 2 again. So that's our next sample. At that point, we will once again sample the slope. This is the slope S2. And then we will follow that slope out a distance h. That gives us the 4th point. We will sample the slope at that point, and that will be our 4th slope. Having done so, we take a weighted average of those 4 slopes and follow that weighted average out a distance h. Now, what is the error of one step of 4th order Runge-Kutta? Well, from the title you might think it's order h to the 4th, or maybe it's order h to the 5 or better. This definitely should be better than Hoyne's method, which is order h cubed, because after all, otherwise we wouldn't be covering it. Well, as before, we're going to do the same thing. We'll have the same 2 initial value problems, and we will approximate y at t0 plus h for successively smaller values of h. So, for example, let's just do one calculation of 4th order Runge-Kutta. Let's approximate y at 0.4 with this very simple initial value problem. So we calculate the slope at the initial point 0, 1, and we get a slope of -1. Now we calculate the slope at t equals 0.2, and y is equal to 1 plus 0.2 times the previous slope. Well, this gives us a slope of -0.8. Next, we calculate the slope again at t equals 0.2, but now the y value is 1 plus 0.2 times the previous slope, not the first slope. Evaluating the function f here gives us this 3rd slope. Finally, we're going to follow this 3rd slope out a distance h. So in this case, 0.4. So t is equal to 0.4. The y value is 1 plus 0.4 times the previous slope. If we calculate the slope at this point, we get that it is -0.664. All right, so now we calculate a weighted average of these 4 slopes. Substituting those slopes into that equation, we get that result there. That works out to be 1 plus 0.4 times the weighted average, -0.824. So that gives our approximation of 0.6704, which is actually pretty good, given that e to the -0.4, the exact value, is pretty close. So let's approximate the solution of this initial value problem at 0 plus h for successively smaller values of h. We will divide h by 2 with every single step, and we will see how the error is reduced. So with h is equal to 0.5, we notice the error is already quite small. With 0.25, the error has shrunk even more, and the ratio is 0.0325. Well, actually, that's pretty close to 1 over 32, which is 1 over 2 to the 5. That's suggesting that the error is order h to the 5. Dividing h by 2 again, the error seems to drop by approximately the same ratio. Divide h by 2, more accurate, and the error drops again by 1 over 32. And again, with each successive step, the error is becoming negligibly small. Indeed, with h is equal to 2 to the -10, we get an exact approximation. The ratio is 0. Well, let's look at our second initial value problem. Again, starting with h is equal to 0.5, we notice that it's already quite accurate. Dividing h by 2, the error has already dropped, and it does look like it's dropping quite quickly. Divide h by 2 again. Again, the error is dropping by approximately 1 over 32, or 1 over 2 to the 5. As we carry on, note that the error is dropping very quickly, each time with approximately a ratio of 1 over 32. And finally, with h is equal to 2 to the negative 9, there's zero error. The approximation is exact to the accuracy of a double precision floating point number. So the ratio is 0. So we'll end there. All right. As before, we note that the error is order h to the 5 for a single step. But as with Euler and Hoyne's method, we want to approximate the solution along an interval, and therefore we will divide a larger interval into n subintervals. And so now we will look at two initial value problems with initial conditions y naught is equal to 1, and we will approximate y at 5 using 2 to the n intervals. However, before we do that, we have to look at our implementation in C++. Everything else is the same up to this point except for the name. We're going to calculate the value of h. Here are our 3 arrays that will store the results. Here are the initial values stored in those arrays. Here's our loop. We will calculate the next point in time. And now we will calculate S0, S1, S2, and S3. And our next approximation is the appropriate linear combination of those 3 values, or weighted average. And we will then calculate the slope at that point. Again, once we're finished, we will just return a tuple with these 3 arrays contained within them. All right, once again, let us approximate the solution of this initial value problem at the point t is equal to 5. So we'll approximate y at 5 given that this solution satisfies this ordinary differential equation as well as satisfying the boundary initial condition y at 0 equals 1. If n is equal to 2, h is equal to 2.5, and again, it's not a very good approximation, which is at the bottom. However, just doubling the number of steps to 4, so h is equal to 1.25, we're getting much closer. The relative error is only about 30%. There's been a significant drop as well. Double the number of points, number of intervals again, the error drops. Double the number of intervals, the error drops. Again, and so we are getting closer and closer to the correct answer. And with each step, the error seems to be dropping approximately 1 over 16. That is a half raised to the power 4. And with 1022 intervals, the error is insignificantly small. Here's our second initial value problem, and again, we're going to approximate y at 5. The correct answer to 16 significant digits is at the bottom. So with 2 intervals again, it's not a bad approximation actually. It's at least 1 significant digit. Double the number of intervals and we're already getting closer. The ratio is, approximately 1 over 20. Double the number of intervals again, and again, the error drops by approximately 1 over 16. As we double the number of steps, each time the error significantly drops. always by a factor of approximately 1 over 2 raised to the power 4. And we're actually getting a reasonably good approximation. All right, so yes, 4th order Runge-Kutta seems to be a reasonable tool. We have far more precision in that last answer than we would ever possibly actually require as engineers. Now, we've looked at 3 different algorithms, Euler, Hoyne, and 4th order Runge-Kutta, and we could compare each of them as to how well they work with 1024 intervals. However, this isn't really fair because, after all, Euler's method uses only 1 function evaluation per interval. Hoyne's method uses 2, and 4th order Runge-Kutta uses 4. All right, so let's just look at what happens with the accuracy if you simply allow for 1024 function evaluations. So for that first initial value problem we were looking at, approximating the value at t equals 5, Euler's method has an error of approximately 8 times 10 to the negative 5. Hoyne's method, with 512 intervals, has an error that is approximately 100 times smaller, actually more than that. And 4th order Runge-Kutta, with 256 function intervals, therefore 1024 function evaluations, has even smaller error, approximately 1/10,000th the error of Hoyne's method. All right, that's pretty good. So for the same number of function evaluations, we're getting significantly smaller error. With that second initial value problem, same situation. Euler's method is not very accurate. Hoyne's method, also using 1024 function evaluations or 512 intervals, the error drops by approximately a factor of 1,000. And 4th order Runge-Kutta, with the same number of function evaluations, although 1/4 as many intervals, the error has now dropped not by 10,000, but by 100,000. So again, a very reasonable tool to approximate a solution to an initial value problem. Another question we may ask is, how many function evaluations are required to get the same accuracy as Euler's method with 1024 intervals and therefore 1024 function evaluations? Well, for that first initial value problem, once again, for 1024 intervals and 1024 function evaluations, we had a reasonably large error nevertheless. We can get that same error with Hoyne's method with only 43 intervals or 86 function evaluations, and for 4th order Runge-Kutta, we can get that same accuracy with 8 intervals or 32 function evaluations. Same accuracy, significantly less work. For that second initial value problem, again, for Hoyne's method, we only need 16 intervals or 32 function evaluations versus 1024. And for 4th order Runge-Kutta, we actually only needed 3 intervals or 12 function evaluations to get the same accuracy, and in fact, better accuracy than Euler's method, with 330 times more function evaluations. All right, so we see that 4th order Runge-Kutta is actually very useful. 4th order Runge-Kutta is actually only one of a class of initial value problem solvers. There's an entire class of these solvers, all of which are called Runge-Kutta. This is one specific one because it's so simple and elegant. However, we're going to carry on by looking at other Runge-Kutta style initial value problem solvers. So following this topic, you now understand the fourth order Runge-Kutta method for approximating a solution to a first order initial value problem. You're aware of the visual interpretation with respect to the slopes for this algorithm. We are calculating 4 slopes and taking a weighted average of those slopes. As you'll recall, the weights mirror or parallel the weights of Simpson's rule, with the evaluations at the midpoint forming 2/3 of the weight, whereas the weights on the two endpoints are 1/6. You understand that the error is order h to the 5th, as we saw, for a single step. You are also aware, of course, that we will apply this multiple times to estimate the solution on a larger interval, but we don't have to do it that often because the error simply drops to order h to the 4. We've seen a number of examples and an implementation, and we understand how much better fourth order Runge-Kutta is compared to Euler and Hoyne, even when we consider the number of function evaluations performed. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!